All right.
Now over to our esteemed lecturer.
Yes. Thank you, Ilya. All right, so welcome back. Hope you had a good walk or whatever else you did during the break. Today, as you know, what I'm going to present is on the non-binary type of gravitational wave sources, continuous sources, burst sources, and stochastic sources or stochastic backgrounds. As you may also remember, one of the things that I asked for you to do would be to read the notes beforehand, and then what we'll do is we'll begin by making a list of questions that you wish to be discussed. And in order to aim this a little bit more directly, let me ask first that the 13 students who are the official students of this course, you have the first opportunity to pose questions for discussion.
I would propose if magnetars could see gravitational wave sources.
Okay?
I have a question about the previous lecture. The magnetic dipole, quote unquote, of the mass distribution.
Yes.
I missed why that can't vary in time.
Because the expression for that gives you the angular momentum, which is not going to change for an isolated system. Other questions about this lecture from any of the 13 students officially taking the class? Just perhaps I should get a bit of information right for myself. How many of you have read today's lecture notes? Okay. I know. They're not binaries. They're not sexy. Yes?
Well, I have a question about mass shedding limit.
About what it is?
Yeah.
Okay.
And maybe one like very hypothetical thing that we discussed, like whether the primordial dark matter black holes can have like different observational properties than other.
Okay. How about if you keep that in mind for Friday's lecture, because we're going to talk about binaries then.
Okay.
Good question. Yes?
In Lorentz straight binaries, if the operation on product gaps can produce a quadrupolar momentum, yes, then we can be source of gravitational waves.
Okay.
Related to lumps that are caused through magnetic fields, do they always come in pairs, hypothetically, on these neutron stars? And whether or not they do, how are they modeled in ways that are more sophisticated than just having some kind of ellipticity to the neutron star?
Okay. All right. Anything else from the students?
So with this supernovae,
Yes.
is there much hope for getting templates?
Is it really possible to think about cosmic strings?
It's certainly possible to think about it. So,
Okay, to try to.
I understand, yeah.
Are there other types of sources that can mimic continuous waves or burst signals that are not supernovae or
Okay.
pulsars?
Anything from non-students? Okay, and you're not forbidden from raising topics as you move along either. So what we're going to do is we're going to go through some of what I consider the most essential aspects of this, and I will attempt to integrate this seamlessly, and you can determine whether I've managed to do that. The first thing that I'm going to do is discuss a little bit of the aspect of yesterday's lecture, which we didn't get to, which I think will help set up some of the discussion, particularly of continuous wave sources, as I do in the notes. So what we're going to do is, you recall that if we're thinking about a moment of the distribution, which can vary, we have to go to the quadrupole moment or higher. And that is going to be on the order of the integral over whatever the region is that bounds the source of your volume element times the density at that radius, whatever it is, times, let's call it Ri, Rj, something like this. And also remember that, as both Will and Ilya pointed out, it's not exactly this. It's actually something called a reduced quadrupole moment, which does vanish for something spherical. But we'd like to get a sense for the magnitudes involved, how strong a signal there is, and so on. Recall that when we were thinking about the amplitude, and the amplitude squared being like the flux, for gravitational waves, it was this little h. Now, this is something that Deidre indicated as like a delta L over L. This is dimensionless. We recall that this has to be proportional to 1 over the distance to the source. But we'd like to have a little understanding of what else it can be. This is dimensionless, remember? So h is something like delta L over L. It's the change in length divided by length, so it has no units. So we need somehow to get this into a unitless form, and we need to get it somehow related to this moment of inertia type thing. So the question is how we do that. First of all, dimensionally, can you tell me what this is, approximately? So in terms like masses and characteristic sizes. Just looking at the integral, what would that turn out to be? And remember, please raise your hand if you have a comment. That way I can focus on it.
Mass times that squared.
Yeah, so this is something like a mass times, let's call it an r squared, which might remind us of a radius, but doesn't have to be. So it's something like this. But if we want to turn this into something dimensionless, then if we're saying that this is, and this is probably a symbol rarely used, if it's something like an mr squared over r, that's kind of an issue. That is not dimensionless. So we need to understand a little bit better about what we can and can't do here. First of all, this is general relativity. That means that we are going to involve some fundamental constants as well. Now the question is, which fundamental constants could be involved? For example, could h bar be involved? This is not a quantum effect, so h bar is not involved. What about the electric charge E? Can that be involved? No, otherwise you're doing some sort of weird melding of the electromagnetism and gravitation. What are the kind of fundamental constants you might be able to bring into this?
GSE.
Yeah, so C, because, well, speed of light's important, and because this is gravity, we've got G. Now, I'm not going to go into this in a lot of detail. Deidre actually accidentally did this in one of the early portions of her lecture. The relativists typically will set both of these equal to 1 in geometrized units. My standard joke at this stage is to note that they do that because relativists have a tendency to have extremely weak wrists, which might break off if they have to write extra symbols, and so they have to conserve their effort. That's not entirely fair. I am sure that there must exist some relativists who have impressively strong wrists and don't mind writing the extra C's and G's. But it does give you, if you omit the C's and G's, there are some aspects of the physics that become a little bit clearer, some of the scalings. And you can always add them after the fact if you know the units you need to get. For those of you who quite properly use unit checks as a way to determine whether you've got a decent derivation or not, that takes some adjustment. So what I will simply assert, and that you can check later, is that in this type of unit system, time, distance, and mass all have the same units. Now, what I mean by that is that, for example, if I take m and I multiply it by g and divide it by c squared, this is a length. So what I mean by these having the same units is that you can take a time and you can multiply it by some combination of g and c to get a mass or to get a distance. But you cannot, for example, turn a mass into a mass squared. If we use that type of analysis, what we see is that we've got an mr squared here, we've got an r down here. if you do this in length units, it's like this is length cubed divided by length. So this is not unitless. We therefore need to divide by something which is like the square of a distance, or the square of a mass, or the square of a time. Any thoughts about what we might do to this in order to get to that unitless h that we eventually need? And one hint, remember, what is it that is required for there to be radiation? Variation. Okay, so with that in mind, any thoughts about what you might be able to do with this?
Going to the time derivatives?
Yeah, so how many time derivatives do you need?
2.
Yeah, so that is to say that you can write this as h being something on the order of 1 over r times partial squared of the mr squared, or the moment of inertia, partial t squared. But we're still not at the stage where we have units that your ordinary non-GR person would recognize. We need to put in the g's and c's. And when we do that, what we find is that it is g over c to the 4th times 1 over r times partial squared I partial t squared. Now looking at this, would you characterize g as a big or a small number? It is a small number. One way of understanding how small it is, I mean, again, remember my very impressive magic trick from yesterday. I'm sure you're still talking about that later, where I was able to spin around faster than 1 over the square root of my density. Now I'm going to perform another impressive magic trick. Now make sure you're looking carefully here. So you see this object here? Now watch this. I am holding this up against the entire force of Earth's gravity. Gravity is really weak, and it only dominates on macroscopic scales, planets, stars, galaxies, you may have. Very impressive. You are an exceptional general. But the reason that it dominates on large scales, of course, is that there is no negative mass. There are negative charges, and so charges cancel out. This means, incidentally, that you can, with outstanding accuracy, essentially say that macroscopically no big object has any net charge. Yes, for those of you who are mathematicians, yeah, a wee tiny little extra bit of charge, sure, but not anything significant. So G is tiny. How about C? Big or small? Big on an absolute scale. How fast can you run relative to C? So this is tiny. This already tells you, again, just from straight dimensional analysis, that you are going to get very, very weak effects. The delta L over L at any reasonable distance from an astronomical source is going to be extremely small. Now, something that you can do if you want to pursue this a little bit more is you can think about, let's say, a circular binary. Now, we're going to talk more about binaries, a lot more about binaries on Friday. But again, I'm giving you the basics here to set up, first, a discussion of continuous wave sources. If we were to think about what this all means, and your I is, remember, something like an mr squared, you can say, well, what is it that we would get for that if we had a binary? So let's suppose, in particular, that we have a binary, and the binary has component masses m1 and m2, and therefore total mass equals, surprisingly, m1 plus m2, and a reduced mass, which I'm trying to make different from my m there, which is equal to m1 m2 over m. You may remember from classical mechanics, you introduced the reduced mass to change a two-body problem into a one-body problem. You can't quite do that in full generality in GR, but it's close enough. And let's suppose you have a semi-major axis that is A, which is the standard unit, as you may know. That means that omega squared, the frequency, so this is Kepler's third law, omega cubed A cubed equals G times M. Now we're going to do a classic astrophysicist trick. See this partial derivative here? I assert that for this, partial squared partial t squared is approximately omega squared. And the mr squared here, which we're getting in there, mr squared is something on the order of mu times a squared. You can convince yourself by limits. It's super helpful to check these. It has to be mu and not m, right? Because if you think about, let's say you've got a dust particle orbiting a black hole at some distance, you should expect that this does not have a particularly large orbital moment of inertia. If you use the total mass, and total mass times a squared, that's giant no matter how tiny the dust particle is. So it's got to be the reduced mass. What this means is that you would put this together and you'd find that h ends up being d squared over c to the fourth, mu over r, m over a. So this is one way of breaking it down. And you end up with something that is a tiny value, which again we'll return to on Friday. Now, before we go to the continuous wave sources and how things are a little different, any questions at this stage? Yeah.
Yeah, when it's possible to make this assumption about the frequency to the second order derivative of time?
Yes, so this is an important question because in terms of this match, this is something that would only work for a binary. But essentially what we're asking is, what is the characteristic rate of change of, let's say, the moment of inertia tensor? I could be a little glib and I could say that this is the only frequency in the problem. And I'd actually not be far off in that. But something you can do, and in fact, I encourage you to do if you haven't done this already, these sorts of arguments, when I was learning these things, often struck me as very glib, right? How the hell do I know this? Aren't there exceptions? So the thing I would suggest that you do is to track this down. Basically, put in 2 point masses and calculate the moment of inertia tensor as a function of time and see how this works. Because those sorts of calculations can convince you that not only this sort of argument is okay, but give you an idea of when those arguments could work and when they might not. But it's a good thing to do. A lot of the buildup of intuition has to do with doing lots and lots of problems the hard way first, so that you can see when you are allowed to take certain shortcuts. Anything else? Okay. So here again, we're going to go back to this original formula, but instead of thinking about a binary, we're going to be thinking about a continuous wave source. You recall that continuous wave sources were one of the 4 categories of sources officially defined by the community. And you might think of this as, let's say, a neutron star with a mountain. Recall, though, that if your neutron star is completely axisymmetric, then it will emit 0 gravitational waves if it spins around that axis and is not collapsing or expanding. This might give you the hint that when you're thinking about the appropriate moment of inertia of your star, it is not the full moment of inertia of the star that is going to be relevant for gravitational radiation. It has to be the non-axis symmetric part. A neutron star has a big moment of inertia, but if it is axis symmetric, 0 gravitational radiation. So that's kind of a general hint that if you're going to take this sort of expression and use it not for a binary, but for a mountain on a neutron star, the effective moment of inertia you care about is the moment of inertia of just the mountain. Now, neutron stars have enormous surface gravities. If you have sort of typical values for neutron star masses and radii, the surface gravity of a neutron star might be 200 billion times the surface gravity of the Earth. What that tells you is that the fraction of the full star's moment of inertia that could contribute to gravitational waves is tiny. You may know this, right? The height of a mountain is kind of inverse to the surface gravity. So even though neutron stars appear to be surprisingly strong in their crusts, you can't have much of a mountain. Okay, so with that in mind, what we're going to do is we're going to take this and we're going to suppose that we have a star that has a lump on it. Now that lump, let's say, has a moment of inertia that is equal to some epsilon times I of the star. Now, so far we are agnostic about how we get a lump. We're just supposing that there is a lump of some sort. So in that case, we have H is going to be something like, again, G over C to the fourth, 1 over R, times omega squared times epsilon times I. But there's one more thing we have to keep in mind. When we have a binary, it's orbiting. That means that if you know the mass, you know the separation, and you suppose it's circular to make it easy for yourself, you know omega. This is where you use Kepler's third law. Is that relation going to hold for a rotating neutron star with a mountain on it? Does this relation have to hold? So if we put in, for example, the radius of the star, must it be the case that omega squared r cubed equals gm?
Not unless it's maximally rotating.
Exactly. And in fact, this already allows us to address one of the questions up there, number 2. Think about what would happen if you have a neutron star, or any object, which is gravitationally bound to itself. So not structurally bound like iron, but gravitationally bound. If you were to have that star rotating this rapidly, and you look at something right on the surface, is that something on the surface going to be bound to the star? In fact, if you go a little faster than that, it would fly off. It would not leave, but it would orbit. So that's the highest rate that you can possibly have. But you can certainly rotate more slowly than that. You could not rotate at all, for example. So this is a way in which you do not couple these quantities when you have a rotating star.
Can you show us your magic and see what your mass shape is by rotating?
Well, I kind of can. Let's see if I have the proper room here. I know. I will terrify the students in the front row and give myself a little bit more room. So basically, if I have my objects here, and I start spinning around, the faster I go, I have centrifugal support. And I didn't even hit you, did I? So I am not, however, so dedicated to my craft that I will spin rapidly enough that my hands will fly off. I'll need them later. So here we have our H. You also can look at the flux you would get, and this is something that I will stipulate, but you can read the notes to look at it. If you have, say, flux with the luminosity, the luminosity has to be proportional to r squared, the area of the sphere at the distance r, times h squared times f squared. Again, you can try to demonstrate that yourself. That means that this, when you end up putting in the proper numbers, you get something like 32/5. So this is coming from nowhere. I'm just saying that it's the answer you eventually get. G over c to the 5th times epsilon squared times the I along the symmetry axis squared times omega to the 6th. Now in this case, what I'm doing is I'm imagining that we have something which is an oblate spheroid, where here you have A and here you have B, and epsilon is defined as A minus B divided by AB to the 1/2. So this is a particular case where I'm going from the idea of a lump to something that's an ellipsoidal. So not a spheroid, but is actually it's triaxial, so that it has a non-axis symmetry to it. But the thing you should note here is the extraordinarily strong dependence on omega. There's omega to the 6th. That means that if you were to spin a neutron star twice as fast and it had the same ellipticity, it would end up having 64 times the luminosity in gravitational waves. This is a property of this type of radiation that has intrigued a lot of people for some time, and in fact, it even led to one of the arguments that I suppose helped get Initial LIGO its final funding. So let me explain. This now relates to LMXBs, and so we're going to answer a couple of questions about that. Low mass X-ray binaries. If you have let's say a neutron star, could be a black hole, but a neutron star in a binary with a companion, and the companion is, let's say, half a solar mass or a tenth of a solar mass, and it's close enough that it can donate matter by Roche lobe overflow onto the neutron star, then it's going to spin up the star, except that it has a lot of other interactions, and Anyway, the question is, how fast are these things spinning? Well, you can measure these in a number of cases. And if you ask yourself how fast could a neutron star spin if it were at mass shedding, it's maybe 1,500 hertz. It depends on details, but it's big. The highest frequency ever, at least officially announced, is about 716 hertz. It's half that. So something has to be stopping these things from spinning as fast as they possibly could. Now, what could that thing be? Okay, so magnetic fields can do it, all right? If you have a strong enough magnetic field, then any matter flowing onto the star couples far enough away from the star that the Keplerian angular velocity is low, and therefore it doesn't spin up past that. Indeed, if you look at the descendants of low-mass X-ray binaries, these are the millisecond pulsars, and they have magnetic field strengths, or at least magnetic moments, which are completely consistent with what you would need to stop the spins from getting significantly higher than what we see. But there's always the excitement possibility, and therefore there have been people who have investigated the possibility that it is in fact gravitational waves that are slowing these things down, stopping them from going really, really fast. Now, one argument would be that because of this very, very high, this very strong dependence on omega, you might have a wall. Okay, rather than some kind of gradual decrease in the number of pulsars at some higher spin frequencies, you might be moving along very nicely and then just basically stop. Now, there are discussions about this. My opinion is there's no strong evidence that there's any gravitational wave involved, but it's an interesting possibility, and we would learn some things about neutron stars if we were to see this kind of continuous wave radiation. But let me try to explain why that is, anticipating a little bit what we're going to discuss on Friday about binaries. A thing about binaries, they have big-time changes in their quadrupole moments. They are strong emitters of gravitational waves, but they're transient. When you have your black holes coming together, it's not that they come within a few radii of each other and decide to just hang out for years radiating. They're going in, okay? These sources, on the other hand, it's not that anything is merging. You just have a lump of some sort on the star. And in principle, therefore, this can go round and round and round and round and round for a long, long time. What this means is that you could have a much weaker source of gravitational radiation, which nonetheless is detectable because it lasts for so long. Essentially, you build up the signal. Now, I can, again, just sort of write something directly here, which is that when you put in these correct factors, you get a characteristic amplitude of 4 times 10 to the minus 24. Remember, this is dimensionless, so I don't have to write units there. Times this epsilon times the period in seconds to the minus 2 times 1 kiloparsec over r. Now that might not sound too bad if you know your sensitivity for advanced LIGO. We're talking about sensitivity that might be just general order depending on exactly where you're looking. The problem, however, is this epsilon. So epsilon is something, this is the degree to which you have a triaxial source. This epsilon is very small. Even if you have an extremely rigid neutron star, it's likely to be tiny. So as I discuss in the notes, and I recommend you go there for additional information, it's a real challenge. In fact, for the best timed pulsars, the actual millisecond pulsars that are not accreting, you can rule out that you would see anything with LIGO, because even if you assign all of the spin down of the pulsars to gravitational waves, it would still be below the detectable threshold. But people are, of course, continuing to look. But as I say, the issue here is, yes?
So you made a point as to why LIGO's funding came through.
That you want me to expand on that?
Yeah, I didn't quite. You're sort of now negating the fact that you ever see these sources.
Well, you're definitely not going to see them for most millisecond pulsars. But there are some sources like, say, the Crab, which technically could have some spin down. But I'll expand a little bit on this. It's part of the sociology of how funding happens. It was known by most people that initial LIGO was unlikely to detect anything. And that's a long time to wait in order to get results. Early on, there are always going to be theorists who suggest that there are going to be sources that are visible earlier than others. In the late 80s, for example, there were some supernova models which suggested you might get a large fraction of the energy coming out in gravitational waves. And if that happened in our galaxy, then we would have been able to see this even with early stages of initial LIGO. If the balance between accretion torque, spinning things up, and gravitational waves spinning things down was in fact the way these are balanced, an argument was made in the late 90s that initial LIGO would see it, especially for the brightest source. I think this was not a likely argument at the time, but it wasn't impossible. And so this is something that was sold as the idea that initial LIGO might see something. And then when that, as expected, didn't happen, there were, I think, some follow-on questions about those population synthesis people. Are they lying to us too? Are we not going to see double compact objects? But fortunately, nature came through. So this is how it works, right? You know in reality you're likely to need to wait, but you don't want to tell people it's absolutely guaranteed you're going to have to wait until you're all dead to see a result. So sometimes you use optimistic theorists.
But the epsilons that you need for explaining the spin down are very large.
Yes, they are.
I mean, a normal epsilon is what, 10 to the minus 9?
Yeah.
You need to push that by like 6 to 7 orders of magnitude?
Not quite that much. You could push it to 10 to the minus 5 and explain some of this stuff. But even that's quite high. But that actually comes down to now a couple of questions here. So when it comes, for example, to lumps, and do they come in pairs, how to model, and so on, there are a variety of things that people have discussed in terms of how you might get lumps. One way is what you might call a magnetic mountain. If you have a neutron star and it has a magnetic field and matter is guided toward the magnetic pole, it's not that it's always going to stay at the pole, because as it piles up, it'll spread beneath. But there is a degree to which you can maintain more matter near the magnetic pole than you would elsewhere. And if that magnetic pole is not exactly on the rotation axis, that's going to give you this type of epsilon. People have also talked about heating processes that can cause density asymmetries. And the degree to which all of this works is unknown, but a lot of work has been done. In terms of lumps coming in pairs, then they could, but you could also imagine asymmetries that would change that. For example, if you have a magnetic field on a neutron star, there's no reason that it must be an absolutely centered dipole. Probably it's going to be offset, right? You see this in planets. And so if so, more matter is going to be on one side than the other, so you can imagine a difference in that sort. So those are a couple of the points to make. Now, anything else about this before I tell a story against myself?
I have a quick question. So, if you have some kind of accretion process that's spinning up, well, sorry, I know you talked, I think you briefly said this in the notes, but then can you effectively have a larger loss of gravitational waves, and you can build up this kind of minimum that you could have for one of these particular systems? So you said there were just systems that are ruled out by ever being able to be detected by advanced LIGO.
Yes.
But can you play with that a little bit if you have something that's countering the?
Yes. The systems that I am saying are ruled out are non-accreting pulsars. There's nothing that spins them up. You can measure their spin down, and you can say this is the spin down energy, a reasonable estimate of the total moment of inertia. So you get an E dot. If you give all of that E dot to gravitational waves, in many cases, you still are below what LIGO could possibly detect. Now, there are other sources where that's not true. For example, the CRAD. And the current rate, so LIGO people, it's beneath 1% of the spin down rate by now, right? By how much? Factor of a few, probably. I think the end of the initial or enhanced LIGO run was something like 2%. So, there are sources like that, but for many you can say it definitely can't play a significant, it can't be strong enough that LIGO would see it. The story against myself. In 2010, I was about to take over as the chair of the LIGO Program Advisory Committee, which turned out to be a wonderful thing, and I got permission to spend a month at Caltech which is, of course, along with MIT, these are the main U.S. institutions involved in LIGO. I wanted to learn things, talk to instrumentalists, just whatever. And of course, in doing this, I was trying to think creatively. And then a thought struck me, a brilliant thought. A thought so impressive that I almost dislocated my shoulder, patting my back, and how brilliant it was. Now, at this stage, I'm sure you're asking yourself, what was Cole's brilliant idea? I'll tell you. So the idea is as follows. I mentioned yesterday that supernovae are not now considered to be very likely sources of detectable gravitational radiation unless they're in our galaxy. They have to be really close, only a small fraction goes. But there are lots of uncertainties about supernovae, so I thought, what if you have a fast rotation inside your supernova? Now, you may know that if you take a classical fluid that's self-gravitating and you have a certain total mass, you have, say, a uniform density, and you give it more and more angular momentum, then it goes from a sphere, no angular momentum, to an oblate spheroid, and then it bifurcates and it goes into a triaxial ellipsoid state. Now, the oblate spheroid emits no gravitational radiation, a triaxial ellipsoid will. So, turns out that if you look at this, you have the Jacobi ellipsoids rigidly rotating. Not only that, but people have actually worked out the gravitational radiation that you would get from them. So, what if every now and then you have a supernova that's rotating rapidly enough that when it collapses into this triaxial configuration, maintaining its rigid rotation? It turns out you can easily calculate the effect, the strength of the gravitational radiation. It's a uniform curve. I was so impressed by my own brilliance that I actually wrote a paper on this in 4 days. And then I decided to check the literature. You might want to do it in the other direction. And what I discovered is that in 1970, Chandrasekhar had come up with this idea. I also discovered, because I started looking at papers that referred to Chandrasekhar in 1970, that he was wrong. So was I, but that's right.
That's not the point of the story.
That's not the point of the story. I'm wrong a lot, but Chandrasekhar, I was a little surprised. And it turns out that something that actually was known in 1970, but that he didn't take into consideration, is that if you have something like this which evolves under gravitational radiation, it conserves circulation. So that the important consequence is that instead of maintaining a rigidly rotating Jacobi ellipsoid, you end up having differential rotation inside the ellipsoid. And indeed, there's a family of ellipsoids going all the way from Jacobi ellipsoids, rigidly rotating in space, to Dedekind ellipsoids, which are not moving at all in space but have pure internal circulation. Okay, so there it was. So it's 4 days of my life that didn't turn into a paper, but that's okay. It's kind of interesting to think about these things anyway, and indeed, this is what I would like you to do now. I would like you, if you could, to form into your groups and address to write a paper in 4 days. No, I'm giving you 4 minutes. We don't have 4 days. Now, here's the thing I would like to pose to you for your groups. So as I said, what begins to happen if you have a sufficiently rapidly rotating proto-neutron star that collapses, it goes into, let's say, a Jacobi rigidly rotating ellipse, and then it starts having internal differential rotation. The question for you to discuss is, what happens then, and what will be the consequences for gravitational radiation?
Can you maybe explain what the differential rotation inside is? So the outside does not rotate, but the inside rotates?
If you go all the way to a Dedekind ellipsoid, the outside is not moving, but inside you have matter moving around.
Which is like in different cells where it moves less and more the more you
Yes, so they're circulating around, carrying angular momentum, and they can do so differently. So they could rub against each other, for example. Okay? Go for it.
So your question is, in neutron stars, actual neutron stars with, say, superfluid cores, or what could happen with gunk?
So suppose you have a real fluid, so your proto-neutron star, which collapses, becomes triaxial, starting off rigidly rotating, but because of the effect of gravitational radiation, starts to become differentially rotating. The question is, follow the evolution from that stage on. What's going to happen? And what will be the consequence for the strength of gravitational radiation? Not quantitatively, qualitatively, of course. Is the question clear, or should I try it another way?
There was some discussion.
Okay.
It will fragment into 2 cores.
All right.
And then I will go with the right paper in 2 days.
All right, go for it.
That's also been published. So
That is something.
But isn't it like
Thank you.
Have your answer? All right. All right, everyone. Sounds like the discussions are ebbing a little bit, so this might be a good time to hear your thoughts. So what would be the subsequent development of our ellipsoid, and what implications might that have for gravitational radiation?
So we thought that the differential rotation of the fluid would undergo Rayleigh-Taylor type instability, and the internal fluid motion become turbulent and quickly dissipate the energy. So any gravitational radiation would sort of be truncated very quickly, rather than slowly dropping.
Okay, interesting thought. Other thoughts?
Maybe we have not just one frequency, but many different frequencies for each.
Produce some internal modes. Mm-hmm. Anything else? Yeah.
If you compare the luminosity as a function of radius to the rotational energy as a function of radius, luminosity grows much faster.
Mm-hmm.
So, I think you just said this, but it has to spin down from the outside in.
Yeah.
Right. So the outer layers will stop the soonest. And I did not have sufficient muscle to actually calculate that rate, but one could imagine just taking that ratio and getting a time scale as a function of r, which will be some power just like r cubed.
Okay. Any other thoughts? All valid points. This, I believe, is a subject that is not completely resolved. In fact, after the 1974 paper by a graduate student at the University of Chicago, where Chandra was, pointing out that he was wrong, there was a literature that developed in the 1970s about this, and all of these various points were made. In addition to turbulence, you could argue that there are effects that would try to lock the rotation generally. For example, what viscosity exists will try to do that. Magnetic fields will tangle and possibly help slow things down a little bit. And therefore, there is an unresolved answer to this. It is likely that you have a competition. The fact that you have differential rotation means that the system would like to get rid of the differential rotation. For those of you who know what hypermassive neutron stars is, when two stars come together, there's a differential rotation that is thought to cease very rapidly because of various effects inside. But at the same time, gravitational radiation is trying to impose differential rotation as long as it can radiate in a significant way. You also have the fact that you don't have an isolated system. It is actually going to be losing net angular momentum, won't just be redistributing it by magnetic fields. People are talking these days about how magnetars might help power some types of supernovae. So I think the answer is that this is not completely known. But I also think that it seems very likely that you're going to get relatively little gravitational radiation, all things considered. But this is not completely known. So good job of thinking about it. Yeah?
But if you don't have magnetic field, the viscosity is very small. It's quite small. It's also quite hot. So the viscosity is higher than it will be later if it's a proto-neutron star. But I believe you're right. And that's one of the main reasons that I am pessimistic about the prospects for gravitational radiation, essentially because you're going to induce differential rotation and not get rid of it. If you had all the way to a Dedekind ellipsoid where you have nothing but internal circulation, you essentially emit negligible gravitational radiation. So I think that's likely to be the final state. Yeah.
Is there an intuitive way for understanding how you get this triaxially rotating thing into the Dedekind ellipsoid or whatever it is?
Are you asking about why you have something triaxial to begin with, or how it is that you end up with internal circulation?
How it is that you end up with internal circulation?
So it turns out that Kip Thorne, a couple of years before Chandrasekhar's paper, demonstrated that under the influence, purely the influence of gravitational radiation, you have a quantity called the circulation that is conserved. If you conserve circulation while losing angular momentum, it ends up being the case that you have differential rotation. I don't know that I can do better than that, sorry. Yeah?
In your note, you said that string stars are somewhat different from your stars because they're self-bound and not rotating.
Yes.
And they are different in this sense, or this kind of argument?
That's a good question. Typically when people have talked about proto-neutron stars that might ultimately end up in this triaxial configuration, they're thinking about stars that are less dense than the neutron star will ultimately become. I believe it would be unusual, unanticipated, for it to be able to transition to a strange star at that low a density. However, when people talk about the ellipticity that an object can have, a strange star could have a considerably larger ellipticity than a neutron star. Something that's self-bound, maybe an epsilon 10 to the minus 3 instead of 10 to the minus 5 or 6. So it might have some influence. Yeah. Anything else? Okay, in that case, what I'm going to do, because I want to also allow you to work on some of the problems, is I want to go a little bit quickly through the idea of bursts, and then since nobody asked about stochastic backgrounds, we're not going to talk about stochastic backgrounds. So in terms of supernovae, the question was, is there any hope? Well, we just kind of talked about it. If you have sufficiently rapid rotation, even if it's a temporary state, it could radiate far more energy in gravitational radiation than if you don't have this type of triaxiality. In terms of these things, continuous sources and burst sources, continuous that are not pulsars, bursts that are not supernovae. So remember that a burst is something which you could kind of define as an unmodeled source of gravitational radiation. It's some excess, but you don't have a template as you would for a binary. You don't have a template like the trivial type you would have with a continuous source. So it's just something else. For that, something that actually has played a role already in the history of gravitational wave detections is that you can have a source so strong that you don't need to model it very well, like GW 150914. As you may know, it was originally detected in the burst search, not the longer and more complex binary search. Also, if you happen to have, and this would be unexpected, an eccentric binary, it's eccentric enough, it would not fit with the circular templates that are being used. But as you have the close passage, that acts as a burst of gravitational radiation. So that'd be an example of a non-supernova type. For continuous sources that are not pulsars, it's not so easy for me to think of that. I suppose you could say that as you have this triaxial thing, if it's spinning down slowly enough, that might count, but I'm not sure that necessarily would. So
At lower frequencies, you can have continuous sources which are not pulsars.
Well, like a white dwarf.
Right, this idea, binary is slowly evolving. That's essentially monochromatic over the time scale observations.
Okay, good point. Yeah, so for example, some of the supermassive black hole binaries that might be seen with pulsar timing arrays are quasi-continuous. So, okay, fair enough. In terms of magnetars, now we can think about this in two ways. First, what if you have the rotation rate? Are the magnetars going to be good gravitational wave sources just based on the rotation? Maybe you have a really strong magnetic field, so powerful that it can cause the star to be lumpy. Now, there's actually evidence of this in one particular case that I mentioned in the notes. Could you do that with magnetars? Well, the problem is this. Magnetars have spin periods of seconds. So not only would this be way below the frequency that could possibly be seen using LIGO, but omega is so tiny that the luminosity is negligible, so that doesn't work. Another thing people have talked about, you may know that, in fact, these magnetars, the first category of sources that were attributed to magnetars was the so-called soft gamma ray repeaters, where you have a burst of some sort. And in fact, people have seen in some of these bursts high-frequency quasi-periodic oscillations at claims of a few hundred hertz in some cases. What about that? Is that a possibility? I am not optimistic about that. Now, why? Remember when we talked about the continuous sources, we noted that this epsilon is tiny, but they last for a really long time. You can sit on the source for years, build up your signal. A magnetar burst, the epsilon is not very large, and it doesn't last very long. So that combination means that I think there's very little hope. However, always remember we might be surprised, and I would love it if I were wrong about that, because that would be really, really cool. And then, as far as cosmic strings, okay, so in various theories there are three types of topological defect in the universe: magnetic monopoles, cosmic strings, and domain walls. Okay, now magnetic monopoles maybe were inflated away. Domain walls, if they exist, sweep across the universe, destroying everything. So we could detect those in a very short time. Cosmic strings, however, are neither lethal nor necessarily inflated away, and they would have the property of being essentially one-dimensional, having a certain mass density, and people like the idea that they might have kinks in them that could produce bursts or continuous waves or something like this. Net evidence, 0. So, aside from the optimistic hopes of a variety of inebriated cosmologists, I don't know that we necessarily think that these things have to exist. Occasionally, we will get little pieces of evidence people propose for cosmic strings. One that happened in the late 80s, which got some attention, is that people were looking at gravitational lensing. Now, you know, if you have a galaxy, you can have a quasar. Quasar's lens, so you get multiple images of the quasar. Well, by gosh, it turns out that there were 2 images of the quasar that were separated by far more than was possible for a galaxy. There was no gravity, there's no cluster in the way. We're talking about like 30 arc seconds. So people writing papers eagerly about how this could be the result of a cosmic string. But there are a lot of quasars. And some of them look pretty similar to each other. And in fact, it was discovered these were 2 quasars that just happened to look similar to each other that were within 30 arc seconds. So they may just be a fantasy. Anything else about that? All right, in that case, because we have, yes?
Maybe this is not, maybe it's out of place, but so you talked a little bit about, in your notes, about turbulence reducing gravitational waves.
Yes.
So imagine that you have an object whose, the kinetic energy carried by the turbulent eddies is comparable to the binding energy of the object.
Yes.
Like an accretion disk. Could you generate significant or losses of gravitational waves that could be, and in that case would vorticity not be conserved, I guess, because you.
Right. The problem with the turbulent eddy approach is that, especially if you think about, let's say, a standard accretion disk where the half thickness is small compared to the radius, the scale of the eddies is tiny compared to the scale of the system. And so this has a few implications to it. First of all, accretion disks are almost never anywhere close to as massive as the central object, so it's already a small amount of mass. But second, you have a cancellation effect. So you end up with actually a very small varying quadrupolar moment. And the second part of your question was?
Oh, and then of course in those systems, vorticity is not conserved.
Yeah, right. It would be, but I think especially the very low mass plus the self-cancellation of the quadrupole moment change, I suspect would mean that it would have a negligible impact. But of course, one of the ways I mentioned this is in the early universe. If you have a first-order phase transition, that you have turbulence and bubbles and collisions and things like that, it might be able to generate some gravitational waves, although it's still likely to be tough to detect. In order to distribute these a bit more, so last time I tried to make it only the students, how about one per group, as you defined yourselves earlier? And there are going to be far too many to actually do in the time we have, but let me suggest you do at least number 1. You might be interested in number 7, and whatever else you see, and then I'll check back with you in about 20 minutes. So 1 per group as you had for the discussion.
So you review and actually you guys have been recording
We're supposed to get 1 per.
1 sheet per group, because I only have 14 of them total. Yeah, so you just share, just discuss whatever problem you want to talk about.
I suppose in that second order correction there, you're massive, you're also not setting it out for speed, right? So there's a difference because of momentum.
He started reading
so you have there's two light loss factors, the protons, but you have a piece where you cancel the so yeah, that's right. Yeah, you're right. Very impressive.
Yeah, or you can look at the web page. That's the idea.
I'm very
The convection
Yeah. So I agree with that. And so if you have an accretion disk,
Oh, yeah.
oh, you're thinking that way.
I've been thinking about whether one can actually make a fundamental display of non-thermal the amount of gas carried binding energy may be related to sun, the atmosphere, the tender line of fire. No, yes, come back to
I mean, you probably have your
some cases you can have the majority. Because I actually think like if you think that magnetic fields are involved,
Yeah.
then magnetic, magnetic fields are separate mass. So can I? Is there a fundamental parameter just to say like fundamental theory exists, and then you can put
So, what would your L thermal be?
well, that would be the only
Anything that is
thermal
Okay. Doubly cool.
but you can like do boundary layers.
and so you've got L thermal, luminosity thermal, luminosity non-thermal. I'm sorry, what is the size of the
And I actually think that that is correlated with the amount of energy that is divided by
Well, obviously, okay, and then we're that's how it works.
No, but we have like another charge.
Yeah, it says supposed that you can start
This. Yeah, one.
Let's say you're thinking about accretion.
No, it's like looking at you, but I can't
So
do that
you've
from
got your
here.
L thermal divided by Well, but that's why I something I really should know power density study, that is very close to stuff I don't know that the observatory flight actually know whether it's good or not, because as you say, it is rare to see something that's important. propagation, you see something looks like a power line, that's a big different power line, you usually don't see the rollover. So you see a power line to stop the propagation. But it sounds like you see that a different picture. Instead of you focus on emerging externally and then scattering it out in the photograph, you got to focus on actually when we immerse into the already yeah, that's kind of what it works. Your operative event is pretty large. You need really efficient weather. It's not really so again, you look at the we're not talking about we're talking about the normal optic the proton bubble, air trouble, the emergency optic. They have to have a lot of protons and it'll spot an outing scatter. I see. So I guess I thought you were saying the actual energy comes out. What distance do you have observation? Okay, cool. About it a little more. I think I wrote a call to order for everything. Thanks.
No, I was just thinking about
Yes.
but you're right, that's the case.
I didn't want to go somewhere else.
I have a quick question, Cole. In one of your questions, you talk about the amount of angular momentum you accrete per unit mass. And the expression you use there is actually based on the assumption that a neutron star, you talk about accretion onto a neutron star, is accreting from the Schwarzschild ISCO. So that presumes that the radius of the neutron star is less than the radius of its ISCO.
Yes.
Are you absolutely convinced that that's close? I mean, because it's actually close. I mean, the radius of the ISCO around 1.4 star neutron star is like 13 kilometers, give or take, right? Which is,
Yeah.
I'm sorry?
3 versus 13.
3? No, but the physical radius is not 3 kilometers.
One solar mass,
Oh, no, I'm not about Schwarzschild radius. The ISCO radius. The ISCO radius is 30 kilometers.
Okay, so interesting question. I have an answer, but I need to call this.
Okay,
to order.
sorry.
Let's talk about it after the break. Hey, everyone. All right. So sorry to interrupt. I hope you have enjoyed doing various things, including, with some of you, destroying Alderaan. Who would like to, from one of the groups, like to suggest an answer to any of these questions? Like maybe question 1, we'll start with it. Anyone do question 1? Yes? All right.
So you just take derivatives of this proportionality, given proportionalities?
Yep.
And plug that into the breaking index?
Mm-hmm. So what do you get for your breaking indices?
5 for gravitational radiation, 3 for
Magnet. Yeah, so 5 for gravitational radiation, 3 for magnetic dipole. Did other people get that answer? Yeah. Okay, and that is correct. And I just want to give a little context to this because as it happens, when you measure breaking indices of pulsars, so you measure omega double dot divided by omega dot squared, you usually don't get 3. Now, it's a very tough measurement. The double dot is especially difficult. You need a really stable measurement over a long time. The problem, though, is, you might get excited, right? Because if it's sort of higher than 3, maybe gravitational radiation has the influence. It isn't. It's lower. In almost all cases, there's one case where it might be slightly higher than 3, but in most cases it's lower. So this has led to a lot of discussion about effects, and it doesn't prove that gravitational radiation has no influence, but it's the wrong direction. Yes?
So what is the general assumption there? Is it magnetic field radiation? Why do they think it's lower than 3?
Well, so there's...
Or is it just not dipole field?
So if it were a higher order field like a quadrupole, it would actually be steeper.
Yeah, okay.
So when people have discussed this, I don't think there is a community accepted answer. But people have talked about various things. For example, winds can, in the right circumstances, give you a lower number than 3. People have talked about continued evolution of the star. For example, the moment of inertia changing as the star spins down and becomes more spherical. The people have talked about these, but there's no uniform accepted answer. So gravitational waves go in the wrong direction, but we still love our gravitational waves. Anyone do any other problem in any of the groups?
Number 7.
You did number 7. Okay. What are you going to say to the emperor?
Well, we were slightly confused about what the question was asking because it said the gravitational waves would be visible throughout the universe with advanced LIGO. So I could just put an advanced LIGO far enough away that it wouldn't sense anything from any given source.
Well, that's not necessarily true. I mean, if you had advanced LIGO and you had a sufficiently large, say, rapidly spinning black holes, you could get them almost to the edge of the universe, so redshift of 1 or something. So did anyone do the calculation for this?
Well, one thing we calculated was to look at what the frequency might be.
Yes.
So we calculated like the characteristic frequency of Earth as
Yes.
a planet, and we saw that it's something like 10 to the minus 5 Hertz. So we wondered whether we needed to dump these basically.
Yeah, so that's a bit of a problem, isn't it? Yeah, and even if you manage somehow to turn the entire Earth into gravitational waves, this is, as it turns out, related to the supernova problem again. And the answer is, unfortunately, you're not going to be able to see it more than a few hundred kiloparsecs away. I don't know if you've gotten used to this, but Dr. Sane tends not to be right. It's one of the ways I try to get rid of my bad ideas, like destroying Alderaan. Any other comments about any of the other questions?
So with number 7, we were more or less thinking of making like an anti-lump on Alderaan.
Doing
Instead
what?
of just blowing up a part of Alderaan.
Blowing up
Creating like kind of a lump, like a continuous source.
Yes.
We didn't get to do the reverse calculation.
So basically what you do is you take its moon and affix it to Alderaan and allow it to rotate. All right. No, I like the way you think. You have a future on the dark side. The challenge, however, is that, again, at the sort of distances here, if you're talking about, say, 3 gigaparsecs away, then even that's going to be pretty much undetectable with LIGO. LIGO is a great instrument, but it's not good for detecting the destruction of planets. Any other comments about any of the other problems?
I attempted number 2.
Okay.
If I read it correctly, you just have to set the accreted angular momentum equal to the rate of accreted angular momentum equal to the gravitational radiated
Yes.
angular momentum. So you have to find what that is.
Yes.
And just using Newtonian expressions, I figured it was basically luminosity divided by omega.
That the energy would be, yeah, that's right.
For the radiated angular momentum.
Luminosity divided by omega?
Yeah.
So that doesn't have the right units. So that has units of right? It has roots of energy.
So isn't energy 1/2 I omega squared?
Yeah.
Or 1/2 angular momentum times omega?
Oh, sorry. So, yeah, duh, yes. So did you happen to get an epsilon out of it, or?
Yes, but I can't interpret it.
No, that's fine. You end up with something like 6 times 10 minus 8 is what you need. Which sounds small. This is one of the reasons why people were in the late 90s thinking that might be, right? You might be able to get a very small epsilon and allow yourself to balance the gravitational waves. So, it's not like these things were obviously wrong. It's just that in detail they don't really work out that well. And Ilya, you were asking why it is that I'm making the assumption that you have the accretion of the ISCO. Is that in fact correct? Because the innermost stable circular orbit for a non-rotating object, spherically symmetric, is 6gm/c squared, which I think you calculated was about 13 kilometers for a 1.4 solar mass star. And the logical question would be, what if the star is a little bit bigger than that? It's not ridiculous to think it might be a bit bigger than that. Maybe 14 kilometers or something like that. Now, of course, magnetic fields make a big difference, but we're ignoring magnetic fields here. One of the reasons that you can get away with this approximation is that the ISCO is a point of minimum angular momentum. That means that if you go a little bit outside the ISCO, you have very close to the same specific angular momentum. So even if it is slightly larger than the ISCO, the net effect is going to be almost the same as if it were at the ISCO. Okay, anything else? All right, thanks. We have a break now. We have a coffee break until 4:30, and then we come back and appreciate Evan.
Thank you.